Before we do that, just a bit of recap. Uh, so yesterday you have seen that using Biot-Savart law to obtain or to calculate the magnetic field at any arbitrary point. So even though it is applicable for, even though there's only one example shown here, which is a line charge, which is a line current, okay, a finite line current. So, however, um, the Biot-Savart law is applicable to surface current as well, and also as well as volume current. Okay, so you will see a few of exercises in your tutorial. So some of them are quite challenging. I mean, challenging in the sense that it's not establishing um, the integral. Perhaps, sorry, the challenges is not first. It is not because of the integral, but the establishing the idea. Um, So you see some questions in a question. In the tutorial. So please try it out under, I think, Biot-Savart law tutorial. But the as long as we manage to find to uh to establish the vector. So what I'm saying is, as long as you're able to establish the position vector from the source, from the contributor towards the point of interest. So again, here eh, here we mention, I always say this is an arbitrary point. So arbitrary point, that means it can be anywhere. Yeah, it is assumed a variable point along the current line, along this wire. So so as long as we able to we manage to establish the position vector pointing towards the point of interest, and the rest is similar as what we have done in Coulomb's law. Okay, so we are going to discuss Ampere Circuited Law now. So I said that it is similar to Gauss law, right? It's similar to Gauss law. So Ampere Circuited Law mentioned that for a current, if we apply a loop, if we apply an arbitrary loop, if we apply an arbitrary loop around a current, so it is mentioned that the line integral, the line integral here is equals to the current enclosed. So so assume that I have a line, a current carrying wire. Okay, so you can take your pen. So imagine that. So that represent, let's say that you put a pen on, you place it on top of your table, perpendicular to the table. So the pen represent the current direction. Okay. So now, so in three dimensional. So assuming that now my current is pointing towards the z, yeah, pointing towards the z in the z direction. So so Ampere's law says that if I apply a path, yeah, a closed path, apply a closed path, a symmetrical closed path. So it will be a circle here, enclosing this current, enclosing this current So the current, enclosing the current line. So the the magnetic field, okay, the magnetic field that work along the path, the magnetic field that work along the path is equals to the charge, is equal to the line current enclosed. So this is Ampere's law. So this is Ampere's law. So how do we apply Ampere's law? Is the same as Gauss' law, but instead of a closed surface, but this is a closed path, not a closed surface. Yeah. So here you can see that it is a circle here. So it's a circle here actually. So this represents a closed path. And the idea of how we apply Ampere's law is the same. So we have to look for current distribution. So the current distribution have to be uniform, okay, and symmetrical. So means that only the line is infinite. If the line is infinite, then only we can apply Ampere's law. So however, again, I want to emphasize there's no infinite line current. It depends always the point of reference. The point of reference where we I mean depends on the point of reference from the observation, the point of interest where we want to determine the magnetic field. So if the point of interest is very much smaller, if it's very much smaller than the line current, then we can apply Ampere's law to calculate um, the magnetic field. So otherwise we can't. So the assumption is it must be symmetrical. So symmetrical means if let's say I have a path here, okay. So the path can be applied in anywhere. I mean this closed path here can be applied in anywhere along, can be applied anywhere along the line current. So it means that let's look at the symmetrical part of it. So if you're standing here, so if let's say you're walking along this circle, let's say you're walking along this circle, observing, looking at the current direction. So if you're walking along this circle here, so you see I mean imagine that. So you see that everywhere is the same, right? So it doesn't change the perception. I mean, the line direction doesn't change. That means the distribution of the current is the same everywhere. It is the same everywhere along this circle, along this path. Oops, sorry. Okay. So the path direction then, the path direction. So how do we choose the path direction? So we follow right hand rule again. So the path direction will be, in this case, if you're using right hand rule, so it will be counterclockwise, yeah, counterclockwise. Seen from the top, yeah. If seen from the top, it is counterclockwise. So use right hand rule. So basically, this path here also represent the magnetic field direction, the direction of the magnetic field. So it means that the magnetic field is actually enclosing or encircling the current. So which is basically produced by the current itself. So the source of the magnetic field, is from the current. So let's say we have a direct current. Direct current means it doesn't varies with time. That means the direction of the current maintain the same, the magnitude of the current maintain the same along the line, right? So the magnetic field produced is also static. It doesn't change. It doesn't change with time. So by using my right hand rule, the direction of the current can be determined as the direction of the magnetic field can be determined, okay, using right hand rule. So that is basically Ampere's law. So by Ampere's law, extending some of the uh, vector calculus theory that we have discussed before regarding Stokes theorem. Stokes theorem relate the the line the line the line integral with the area, enclosed area. Okay, so the line integral with the enclosed area. So this is Stokes. This is basically application from Stokes theorem. So the line integral, it is related to the surface integral of the area. So this area here, enclosed area. So this area here represent the path enclosed by the I mean the area enclosed by the path, yeah, by the path L. And so this is the area enclosed. So area enclosed by path L is S. Okay. Area S enclosed by path L, yeah, the closed path. And then subsequently we can relate the enclosed current as the current density, which is J. So the current density is the current density definition, J, is current per unit area. So J is, bear in mind, J is current per unit area. It is current, current amperes per meter square. J is ampere per meter square. So this is true, yeah. So this is true, right? So that means the current, the effective current. So the dot product basically it means that. So what is the effective current that passing through the area? So the current direction may not be perpendicular, may not be perpendicular to the surface. It could be at it could be at an angle. Okay, so what is the effective current? So we need a dot product. That means we need the effective current that passed through the surface area. So after we apply that, after we apply Stokes theorem, so we can compare now this term. We can compare now this term with this term. So basically, both are surface integral or double integral. So they are identical basically, and by comparison, J is equals to the curl of H. Okay, J is basically the same as the curl of H. So we have seen similar concept in electric field. So the electric field I mentioned. So when we apply, if let's say the electric field is conservative, so if we apply a closed path, so the work done is zero if let's say the electric field is conservative. And similarly, we also apply Stokes theorem, and we have a condition where the cross of E equals to zero. So it's also Maxwell equation. Okay, so this is electrostatic field. So by comparison now, so if you can't remember why this happens, please refer back to the notes. So now we have Maxwell equation for magnetostatic field. The curl of H, the curl of the magnetic field is equivalent to the current density. So if let's say we are given a magnetic field, so we want to find the current density in that medium, or inside the medium, so we can perform the curl of the magnetic field, and therefore we can determine the current density in that medium. Okay, so application of Ampere's law. So for Gauss surface, we call it the Gaussian surface. So for Ampere's law, the name is quite similar. So we call this, the path is called the Amperean path. So enclosing, so the Amperean path will be, we have to apply a symmetrical path. So same as how we apply Gaussian's law, Gaussian surface. So basically, if we see a symmetrical charge distribution, let's say, then we apply the Gaussian surface, which is also similar to the charge distribution. So if it's a spherical, then normally we apply a spherical Gaussian surface. And similar, if let's say a cylindrical, then we apply a cylindrical Gaussian surface. So for current, which is a line current, then we apply which is also a circular path, which is similar to the cylindrical like a cylindrical path. So now so the radius of this Amperean path, which is a circle enclosing the current, we assume that any is arbitrary, right? So it's arbitrary. So the circle, the line integral. So basically, the we assume that because since we have chosen that this path here, as I mentioned just now, it is symmetrical. It is the same at any point you stand by looking towards the current. So it is the same. It never changes. So therefore, it is symmetrical. From the point of observation on this Amperean path, it is everywhere the same. by looking towards the current. So it means that the magnetic field is also along this path. So the direction of the magnetic field is also along this path. So in a sense that the dot product vanishes. That means the 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 direction of the magnetic field is, it is phi, in a phi direction, encircling the current. So here you see the current enclosed involve the phi component. So the cylinder coordinates, we have radius, we have phi, and z. Okay. So the phi component, so other components doesn't exist, because due to the fact that, as I said, the Amperian path that we apply. So the point from any point of observation, on the path looking towards the current direction is the same. So it doesn't changes the current. So the your point of reference, any point of reference along the path, when you look at the current, is the same. So if it's phi, then so dl here. So dl. So what is the, so if this is fixed as rho, if this is fixed as if this is fixed as the I mean the radius as rho. So I will put a remark here. The radius of the Amperian path is rho. Okay, is rho. So dl, so which is infinitesimal path, right? Is a infinitesimal length here, infinitesimal arc on the path. So therefore dl, okay, it is rho d phi. Okay, so it makes, so this d phi here, at what direction? So at a phi cap direction. Okay, at a phi cap direction. So counterclockwise direction. Counterclockwise direction, looking from the top. Looking from the top, counterclockwise direction. So therefore, the dot product of the phi component. So a phi component dot a phi component. So it is a constant now. So if it's a constant, then I can factor out my magnetic field component, my magnetic field component, the phi component, outside the integral. And if I integrate along the path, so one full revolution to make a closed path, which is 0 to 2 pi, and therefore we get the result will we get 2 pi rho. So rho as well, rho is constant. So basically rho is constant. So we are actually integrating phi. So eventually we get the magnetic field produces by the current, is I divided by 2 pi rho, or 2 pi r, yeah, in the rho direction, in the phi direction. So this is similar. When to the special case when we say, I mean, the infinite line, when we apply Biot-Savart law. So we can, so let me bring you back a few slides earlier, just that you know. Yeah, so we have a similar situation at this point. So when so as I demonstrated yesterday. So as B tends to infinity, negative, and A tends to negative infinity, so the magnetic field is reduces to the current I divided by 2 pi rho, right? So rho basically is the point of is the radius measure, the point of interest is the radius measure perpendicular from the current, from the line of current. Okay, so I have demonstrated to you. So basically, from Biot-Savart law, in the special scenario where it is infinite, when A and B tends to infinite, so the expression of this reduces to this. Okay, reduces to this. So same as Ampere's law for infinite line, for a very long current carrying line. Okay. So what about surface charge? So here, if a sheet has a uniform surface current density, so bear in mind the current density that we are looking at uh, is the dimension of the current for surface current density is current per unit length. Okay, so the dimension is given to you is current per unit length. So the surface current now, so you have a let's say imagine you have a paper. So normally this your paper actually is a conductor, most probably, because the only conductor can have the ability to conduct current, right? To conduct current. So to produce current. So the motion, I mean, is due to the motion of charges. So now we assume that we assume that the current is directed to the y direction. So we have a surface current like this. So applying Ampere's law. So here you see that okay, let's say I will draw this. So imagine now you are looking towards this direction, yeah. So I will redraw this. Okay, so I will put a remark here again. View. Uh, so looking towards looking towards the direction of current. So looking towards the direction of current. Okay, so this is the front view. So this is the front view. So that means I put an arrow here so that just to say that that means I'm looking towards this arrow here. That means I'm looking towards the direction of the current. So that means this is my view now. So the one that I draw now, the one that I've drawn here, represent your view. So the dot, so I put the circle with a dot that this basically represent the current direction. Of course it's not separated, yeah, they are not isolated like this, just a representation, yeah. So it is not really, this line here it is not isolated from each other, it is basically continuous. So that means this gap here, do not imagine that this gap here is there's one line current here, one line current here. It's not, yeah. So please bear in mind, this line, it is separated, just a it is just a representation, yeah, to represent that, okay, this surface carries a surface current. That means, so imagine that there's no, I mean, that means the line is the current from one line to one line, I mean, to from the for the representation. So when I say continuous, this between the line, there's no gap, yeah, there's no gap actually. So everything is continuous on the surface, so there's no gap. So same goes for what I've drawn here, is just for illustration purposes. So that means there's no gap in between, it cannot be seen, we cannot assume that the surface current is separated. That means that, okay, here got current and in between here there's no current. No, it's not that. So everywhere along the surface, in pointing in the y direction, at any point on your surface, there's a current pointing in the y direction. So please bear in mind that. Okay, so we have this surface current. So assume this is infinity, positive infinity, and this is negative infinity, yeah. So since we want to apply Ampere's law, so I mean, if you want to apply Ampere's law, that's the only way, right? That's the only way. The assumption we have to make a valid assumption. So the tends to infinity part is from the point of observation. So if the point of observation, so let's say this is my point of observation, that I'm going to circle this. So if this is my point of observation, the one that I circle, is close to the surface, point of interest, point of observation. If my point of observation is close to the surface current, then if it is small enough, it is close enough, okay, that means even though this is I mean, I have always emphasized, there's no such thing as infinite structures. There's no such thing as infinite surface. So it's always referred to the point of observation. So if this point of observation enable us to make an assumption, that the surface is infinite, then we can use Ampere's law now. So Ampere's law says that, okay, so how we choose the Amperean path? So again, if the point observation is close to the surface, so we can apply Ampere's law. So the Amperean path in such a way that the point of the point of observation must be the same. So So imagine that we walk along the path. So everywhere must be the same. So let's say we first enclose this, not really enclose these two. So just enclose, a few of them. So now, um, so how do we determine the direction of the magnetic field? So again, use your right hand rule. Right hand rule. So the path direction, again, the path direction also follow right hand rule. The path direction also follow right hand rule. And then, okay, so since this is a flat surface, the Amperian path, the geometrical, the path geometry must be must be allowed with some symmetrical property. So a rectangle will be suitable for such distribution, for such surface current distribution. And here now we will apply right hand rule. So imagine that. So from this, let's say this current, okay, this current here, it is pointing out, right? So for every current element is pointing out. So um, I try to redraw this again. If you use your right hand rule, so let's say this is the point of interest. Uh, so this is my blue. So if I use right hand rule, then the thumb represent the direction of the current. So curl your finger a bit. Um, I don't know how to draw the finger. I don't know how to draw the finger. So let's say. So let's say. Okay. So this part here, the one that I draw, represent the curl of your finger. See. So your thumb is pointing towards the current direction. So therefore, we can see that the magnetic field, at this point here, the magnetic field is this way, right? The magnetic field is pointing this way, contributed by this current. And another one will be, so let's say I put a color marker so that you can distinguish them. So another one, so again, use your right hand rule. So I will just draw it temporary, just to show that. So use your right hand rule again, and this portion here is your finger, right? This portion of the remaining of your finger, this portion here. So that means now the magnetic field direction is here. So if I'm considering that, these two line current, is symmetrical with each other, that means from the origin to here, the distance is the same, and from the origin to here, the distance is the same. So they are symmetrical about the z-axis. So if they are symmetrical about the z-axis, so my magnetic field direction, it will be as such. So if let's say I have this magnetic field direction contributed by this line, by this current element, and another magnetic field contributed by this current element, and they are the same everywhere, right? So this the magnitude of this current element and the magnetic field of the current element, the magnitude of the current element is the same because it's uniform, right? So this is uniform. So this is the same magnetic field, but different direction. The magnitude of the magnetic field is the same, but the direction is different. So we already know we can decompose this vector here. So if I decompose this, so the vertical component after decomposition, after the vector decomposition, so we see that the this component here and this component in here is cancelled off. Is cancelled off, and only the component which is uh, horizontal, which is pointing in the x direction, which is pointing in the x direction. So back to so this is only, I mean, I've only illustrate two current element. I only illustrate two current element here. So if I'm going to extend a few more, the result will be the same, right? The result will be the same. So there is a field argument here. So I use this as the XYZ axis as my point of reference. So uh, which is along the Z axis. So what about others? What about other axes? Yeah, I mean, what about other position? So the thing is, we already assume that first we assume that it is infinite, right? So when it's infinite, everywhere will be the same. Everywhere will be the same. So regardless where you choose. So if the point of observation, uh, if the point of observation is close to the surface, that means and the dimension of this surface here is large compared to is very large compared to the point of observation. So it means that regardless where we choose, I mean, we can choose our point of observation here. We can choose our point of observation here. So it means the same, because even here, if let's say I move my point of observation to here, so I have infinite. Let's say I will assume back that this is my I mean, I have symmetrical current element along the surface. So it is the same. So of course there's a flaw in, I mean, there's some kind of a flaw in our argument. But when we want to apply Ampere's law, so we will make sure that okay, it is only applicable where it is not at the edge, right? It's not at the edge of this, it's not at the edge of the surface current. So we don't choose this type of point, because so normally we will choose about around the center of the surface current, because um please list, I mean, I will always repeat this: the surface is never infinite. So it is only from the point of observation. And of course, if we want to use Ampere's law, which simplify our calculation, then we have to justify our choice. We have to justify our choice. So if it's close to the surface, and I mean, we shouldn't choose somewhere is at the edge here. like the H at this, which I have just pointed here. So we shouldn't choose this type of position to determine the magnetic field. So now, so I just mentioned that the direction of the magnetic field is only pointing towards the x-axis now. So at the top, at this top position. So the path here, so the direction of the path, and the direction of the magnetic field is the same. So the line integral, here will be the magnetic field multiply the path length. Okay, so since they are the same. So what about these two paths? The vertical one. So what about these two paths here? The vertical one. So the vertical one, there's a path. What is there a magnetic field? Is there a magnetic field in around this region, around the region of around this region here? Is there a magnetic field? So there shouldn't be, right? So because I just mentioned that the vertical component cancel off, and therefore there's no magnetic field in the vertical component. So in a similar region. So at this around this region that we want to determine the magnetic field. So same goes for the below position. So the same argument. So I will draw the line again. So the magnetic field direction contributed by this current element is pointing towards here, and this will be pointing towards here. Okay. So again, the vertical component cancel off, and therefore both components is only contributing at the horizontal direction. Okay, the horizontal direction. And again, this direction, the magnetic field, the net magnetic field direction is the same as the path applied. So again, we are going to multiply the magnetic field intensity with the path length. Okay, the path length given is A and B. So this path length here, uh, so this path length here is A, and the path length here is B. Okay. So it means that I will multiply h of x. Okay, that means from here on my left hand side, I can write this as h of x, okay, times a, so the path length, plus, so one is negative h of x multiply with negative, the path length also pointing in the negative direction, right? So the dot product will be a as well. So it's equals to the current density multiply the length. So it will be 2hxa equals to kyb. So the current density is, for surface current density, it is amperes per meter. So current per unit length. So how we find the charge enclosed is that the current direction, the surface current, multiply the path length that is passing through the passes through the Amperian path, the defined Amperian path, which is this length here, b. So that represent the current enclosed. So therefore and therefore we will have okay. Sorry, not A. My mistake. Sorry, it's not A. Yeah, it's B. Because multiply this path here is B. Sorry. Okay. So as a result, so we can find that the magnetic field at any point uh, on on the surface, on the surface here. So let's say this is your surface current. So at any point here, is represented by half of the current density. Okay, half of the current density. And same goes for here. But of course, so this is your z equals to 0. So this is z greater than 0 and z less than 0. So the direction, I mean, I shouldn't put a cross, just not to con. So the magnetic field, so is always pointing in this direction. So above the surface current, yeah, above the surface current. This is the magnetic field direction. So magnetic field direction above the surface current, and then here is above the surface current. So here is the magnetic field direction below the surface current. Okay, below the surface current. So I mean, it is everywhere. Yeah, it is everywhere. So again, of course, what is the distance here? So what is the distance between? The point of observation. What is the distance here? Again, we have to make sure, remember that during our evaluation, the point of observation is close to the surface, so it cannot be too far away from the dimension of the current. So even though, I mean, most of the text that they will, most of the textbooks that they will tell you that, okay, is everywhere the same. Everywhere above the surface current is the same. Everywhere below the surface current is the same. So same argument when they mention when they mention about the infinite charge, infinite surface charge density, that is applicable to the capacitance structure. So they, most of the textbooks say, okay, the charge density, it is infinite, and therefore all the electric field above the surface is the same. But we have to be aware of this, as I already told you, that the dimension, regardless of how the charge distribution or how the current distribution is always finite. What what justify the infinite is the point of observation. So when they say above, everywhere is the same above the surface current, it's not correct. It's actually at the proximity of the surface current. That means close to the surface current, everywhere is the same. This is what it means. So therefore, so the magnetic field from the infinite sheets of current density is half the current density direction multiply the normal unit vector of the from the current. So at this point, the normal in this case, so I have a y direction. Y crosses z, right? Y cap crosses z cap is my z cap is the normal to my surface, right? So it's x cap, right? Y crosses z, so it's my x cap. So therefore, it is so in general, we can say that the surface current direction crosses with the normal direction from the surface, produces the magnetic field direction. Okay. Okay. So we already time. Okay. So we'll continue our discussion next week. Okay. Thank you, everyone.